agreement somehow. So we expected some
So the actual date doesn't matter in a sense. You have to get the documents.
yeah.
Whereas if you can, I would say the more.
I'm sure.
There are people, you do meet people who like it, but with a group I hang around with, and also the newspapers that they just ridicule people.
Is it visible?
I have one question. Actually,
Would you please start?
figuring out how these different people are approaching. I got to the point where
Okay, so today I'm going to speak about checking global identifiability. This is trying to work with Hong Kong, Alexey Ovchinnikov, and Chia. So before I introduce the identifiability itself, let me show you just one example of a biological model. This is predator-prey model. So what does it mean? It means that like you have a forest, there are rabbits and wolves, and there are some natural interactions between them. And how is this model constructed? So let x1 is number of rabbits, x2 is number of wolves, and you think that okay, rabbits they born new rabbits, and this rate is proportional to the number of rabbits, and each time that the rabbit meets a wolf, okay, rabbit might disappear. So this is the second term. Okay, so then like modeler constructs this model. He has this sort of reasoning, but he or she doesn't know the values of corresponding parameters. And if you want to really apply this model to any predictions of future, you have to know these parameters, because otherwise it doesn't make sense. So the question is, can we get them from some observations? And the situation might be a bit more complicated if, for example, you cannot measure x1 or x2. For example, rabbits are too fast and too small to count them actually. So, for example, it might be that you can observe only x1 or only x2. And then you have a question, can I get these all numbers or no chance? So this is actually more or less the general identifiability question, how it's it. So you have kind of model
What's the answer there? Give an example. Can you tell me what the answer is?
I will tell later when I give definitions. So
suspense.
Suspense, yes. Some intrigue. So okay, so the main question is you have this sort of model, and you know that you can measure some things and some you cannot.
For that example, the answer is not obvious. Do you or do you not?
Yes, for the previous example, the answer is not obvious, and I will discuss it. So it's even a bit non-intuitive. So I will talk about that. So and you really want to somehow understand which parameters can you in principle find if you have noise-free accent measurements, and which parameters you just haven't any hope to find. Okay, so and in this situation, when I say word parameters, as you have seen in the previous example, you have two kinds of parameters. One type is parameters that appear in equations and govern the dynamic, and another type is initial values. So if you want to model the situation, you have to know them both. Okay, so
Why? Why do you have to know?
If you want to model the whole situation, I mean, you just want to know where to start.
Well, if you, it depends what you want to find out.
Yes, of course. Maybe you are just in some certain parameter. The situation might be different, but you might be interested in both them and them in principle.
Okay.
So, but sometimes your interests are somehow restricted because, like, you don't care about some things and you care more about other things. Yeah.
But there are, what you're saying actually, are you saying that there are frequent situations in which everything has to be known?
Yes, okay, there are such situations.
But not always, but
Not always.
But these are important situations.
Yes, yes. Then you want to simulate the whole thing. So, yeah, correct. Okay, so just to give some very simple toy examples, then like you have this equation x dot is equal to x plus k. Then of course, if you can observe k, if you can observe x, you can find k. Obviously, because like you can just write this and measure x and x dot at every point that you like, and that's it. And to have example of the model that is not identifiable, it's a bit stupid, but if your k is actually sum of two different k's, then you cannot just distinguish between them. So this is just because there are infinitely many possibilities. So I will give formal definition, more non-trivial examples later. Actually, our first example is much less trivial. So
Would you be a little slower for people who haven't seen this before?
okay, sure. Okay, so yeah, so in this situation, the second model I can find from some measurements k1 plus k2 as one whole entity, but I cannot distinguish them. I can just take something from k1 and put it to k2, and observer will not notice that. So that plus one here, minus one here is the same observed behavior.
And so you're claiming that you can deduce it by just looking at this, but what you're going to present will address cases in which you cannot say that.
Yes. So this is kind of artificial example just to first
illustrate the notion.
Yes, see the notion on simple situation, but there are very entangled systems there. It's hard to predict what is actually identifiable.
So
And I want-
together K1 plus K2 would be what I was talking to you about, an aggregate variable. So you can determine K1 and K2, but you can determine the sum, and it's their sum that affects the outcome of the equation, the population.
That's correct?
Yes,
So
and
why do you want to separately determine K1 and K2 if you're only interested in what the system's?
yeah, this is like see. First, you want to detect.
Huh?
I wish you came
Yeah,
to
I know.
Yes, it was actually discussed yesterday by
Yeah.
Nikke.
Example, but in other examples, there are cases where you would want to distinguish, but in this toy example doesn't really
Okay.
make sense, yeah.
Yeah. So, but anyway, before try to find any remedy, you have to diagnose that you have a problem.
Right.
So first you have to find that you have such situation, and then you do change of variables, reparameterization, or whatsoever. But first you have to find that. Okay.
This is also maybe one of the easiest examples that can be explained without technicalities.
Oh, okay.
So this is the reason. But it turns out, as you point out, this example serves several purposes. So it's a really good example, actually.
Simple example is always the best.
Especially if it serves several purposes.
Yeah, I would write K1 plus K2 plus K3.
Great. Thank you.
Okay. So before I give formal definition, I want somehow to introduce with what kind of equations do I work, because in the models that we have seen, usually you don't have kind of complicated differential polynomials or such things. You have equations of very specific, but actually very wide and expressive form of this form. So you have variables x, okay, x, y, and u and mu are all vectors. Okay, so they're bold. So x is actually state variables that somehow define the dynamic of the system, and in general you don't know them. What you know are y's that are observable output variables. So they might be some functions of the state. This is what you can really measure. And u is an input, so maybe first, before doing any measurements, you can maybe apply some force on to the system, the force you know and you choose, okay, within some restrictions. So y's and u's, our friends, know them, and x's in principle are unknown. And so total vector of parameters, it consists of two parts, of mu parameters that appear in dynamics, here and here, and of initial values. So I will not speak about input that much. Almost everything what I will, actually everything what I will talk about works with presence of input. Just to simplify the presentation, I will omit it in.
So are you going to talk about control theory then?
Control theory is one of possible applications of all these
Not
techniques.
the other way.
No, I
Because
mean,
the control theory, we have studied this kind of system.
yeah, sure. Yeah. But in control theory, again, you
Observability
have.
and all that kind of thing, right?
Yes. Control theory is. Well, I mean,
They have used differential algebra already by looking at transcendent degrees and.
yeah, sure. I will mention this people from control theory. This is, yeah, but in some sense, this language it's very expressive. You can speak about control theory using this language. You can speak about biology. You can speak. So this is some general setup.
William, could you repeat your question again? What was your question? Could you repeat your question?
No. See, there's no question. I'm just
There
seeing
was no question.
the connection that people have studied these dynamic systems. Well, they don't call it dynamic. It's control system. So the U's are the inputs, for example. So it's observable. The Y's are the outputs. So they're observable. The X is internal state, black box, inside the black box, right? So they were expressed by this kind of equation. The Y equation is some kind of a constraint. Maybe you want to feedback that. I mean, U could be also Y if you want to do feedback. And the way they do that in differential algebra, and that was done by Flees in the 1970s, right? And so they use, so you put in this X, Y, U, all right? And then you look at the transcendent, a differential transcendent basis, basically, to let's say invert the problems. They have input observation, observability and that kind of thing that they study. I don't know whether this is, connected to what you're saying. That's why I'm asking that all.
So you had a question.
Okay, and he gave you an answer.
Are you going to do an example to show, like, given a system, what each of these variables are in that system?
Yeah. Next slide.
Okay.
I hope. Yeah. So we have a system exactly of this form. We have only one x, one y, and three parameters, so mu1 and mu2, and initial value of x. So this is kind of when x is linear, then y is also linear, and this model can be solved exactly. Just you can write the formula because linear function, and then you see that this example is an elder brother of our earlier unidentifiable example, because in your observed variable y, again, sum of two parameters occur. And again, you don't have any way to split them. So this is a little bit more obscure identifiability. It might be even more obscure, much more. So, but this equation is all the form we discussed. So we have state variables, differential equations in terms of state variables, and then we have output y written in terms of state variables and parameters.
So William, so you were proposing in that sort of easier example to replace k1 plus k2 with a new thing.
Yeah.
How would you do it now?
I don't follow your question, sorry.
So, okay, let me repeat the question.
Repeating doesn't help me.
Okay, let me clarify the question.
Okay.
May I clarify the question? So, do you remember the example of k1 plus k2?
Yeah, sure.
Okay, and you made the proposal to replace k1 plus k2 with something new, relabeled.
Yeah, that's right.
Okay, so
Let's call it
remember.
K.
Okay, so this example has some similarities.
Yeah.
It also has a sum of the parameters.
Yeah, right.
How would you act in this case?
Now, in this case, it actually explains why you don't want to make them as an aggregate, even though the system behavior won't change if mu2 plus x star don't change. But since mu2 and also X star has different physical meaning,
Mhm.
then you do want them separate. And when X star is an initial condition, initial how you start, whereas mu1 is actually a rate. In a sense, technically speaking, the two shouldn't be added together because they're different dimensions. Numerically, fine. I mean, you can always have 3 plus 4. But if 3 is a rate and 4 is a value, initial like population, then you should be able to add them. It doesn't make sense.
No, but I mean, if the initial system makes sense, then its solution also have to make. Doesn't it? I mean,
So mu2 is not a rate. You see, it's added to the.
No, mu2 is X dot. That's a rate.
No,
No,
mu2.
no,
is
no, no.
Oh, the mu1.
No.
Oh, I'm sorry. Okay,
Mu2
okay,
is, so to speak,
okay,
bias
sorry.
or
Okay,
shift
I
or.
misread. Sorry about that. I misread.
Right. Okay. So they could be added. So
Yeah, that could be it.
So
Sure.
is it a puzzle or is it how to? Is it
Yeah,
possible
then you
to-
can then you can lump them together.
So it's not possible to rewrite the system in such a way that.
Yeah, because
Oh, sure. You translate the variable. You just translate the variable by mu2
So you make a
and put
substitution.
them into the initial condition.
yeah, so William's right. If you replace x plus mu2 with x tilde,
Yeah.
then the system will be the same. But this is different change of variables that was previous.
Different kind of change.
Different kind of change variables. So
Well, no, it's still an aggregate variable. The two together is still an aggregate variable. And a lot of systems, the whole idea is to use dimensional analysis to find as few aggregate variables to express the same system in terms of behavior, not in terms of how many variables there are. And in terms of the algebra, you're really saying, what generates the solution, the generic solution of the differential field.
And so how would you approach work in this case?
Yeah, I would do exactly that. I would do a new change of variable with x plus mu2, but mu2 is still unidentifiable, so, I mean, it's like.
Oh, yeah,
the
mu2 is still,
conversation
of
from
course, it
yesterday.
is not
It's like
identified.
the.
But as
yeah.
far as,
Mhm.
let's say, the numerical growth of x,
Right.
it doesn't matter.
Right, right.
Great.
okay, thank you for discussion. So and now positive example that actually will be. I will use this example throughout the next slide. So in this situation, x grows exponentially, and you observe x plus something, plus some shift. So in this situation, again, you can write a solution because, okay, you know that this exponential function, and this is how does y look, and then actually using just this formula, you can find formulas for all 3 parameters. I will do it for you. So you can differentiate 3 times, and then you see that y dot and y double dot differ just by mu1. So the ratio at every point is mu1, and then you can find x star, but by measuring the derivative at 0, and then you can find mu2.
I believe this is in control theory, they call that the invertibility problem. Whether you can invert.
Yes, I mean, since this identifiability question raised in different fields, they have several names
Yeah.
in principle. So I will stick to
Sure.
word identifiability today, just not to.
No, but the point is that, no, if what I said is correct, I'm not a control theorist, okay, but if what I said is correct, then what you should do is to look at what people in control theory have done. Because they have used differential algebra.
Yes, I have looked,
Okay.
and I will cite them in
Okay.
several slides. So far, I just explained the definition. I didn't have chance to mention anybody.
Okay, so I'm going ahead of.
Yeah, I will mention Fleece and Diop and these good people. So what I want to point out right now is that all these formulas have denominators. So in principle, this nice scheme of finding parameters might fail if some of the denominators vanish. So what we'll talk today about is identifiability in generic case. So generically, they don't vanish. So if you have like mu1 is equal to 0, it's very, very special degenerate case, and your exponential growth is actually constant. So today we will speak about what happens generically, because like this non-degenerate situation in principle has probability 0. But I don't want to say that this is not interesting, not important problem. I mean, sometimes you just set some initial conditions and then you set them, degenerate, and this is another challenging thing I just will not talk about today. I will talk about generic situation. You had a comment?
No, but you see, all you need to determine these three parameters is, in fact, at one single time, one point, one data point. Right?
Yeah, one data point is
One
enough
data
for me.
point.
It's more subtle than that. So if you're able,
Well, of course, I mean, that varies. I mean, the measurement is not accurate.
William, the derivatives, it's, if you can calculate the derivative at a particular point,
Oh, yes, of
then
course.
great, yes.
Of
then
course, of course.
That's right what you're
Right,
saying.
right. But you see, so if one white dot, which is that right? You have white double dot, white dot, is that correct?
Yes.
Okay. If one white dot at certain time is 0, but at another time is not, and the same, you know.
Yes,
then
yes.
that will be okay. So-
Yes,
Correct.
it's
So-
vanishing
so you don't-
as a function, William. It's vanishing as a function.
Yes, yes. I mean, as a function,
All right.
yeah, and actually, I mean, if mu1 is 0, then the system is really unidentifiable, because then
Yeah, that's true.
x is constant
Yeah.
and mu2 are constants, and you cannot separate them.
Right.
So this is really an issue. In this degenerate case, situation really changes.
Right, of course. The equation is different.
But however, in practical problems, knowing this generically is sufficiently interesting.
Yeah, it's actually usually the case, because all quantities are not actually not exact, and they
Okay.
usually don't vanish your certain polynomial, which is denominator. So this is what I said about probability 0 principle. So yeah, so today I will speak about identifiability for generic parameters, and this is exactly the reason why I will do that, because otherwise things really change, and this is really a bit different problem. So and here we are, we're at a almost formal definition. So I have this system, I take one of its parameters, theta sub I, and I will have actually two notions of identifiability, global and local. So I will mostly use global, so you can, if you want, you can ignore local, but it's also interesting. So it's a global identifiable if I have these two polynomials. Let me explain what do they mean. This p of theta means actually some polynomial that vanishes on all degenerate cases.
And non-zero polynomials, you pick non-zero.
Yeah, non-zero. Yeah, I pick two non-zero polynomials, of course. So, like, if I can identify such degeneracy loci for thetas and some differential polynomials, a polynomial in use in their variables that somehow captures degenerate inputs. So if I can find such,
You haven't finished the definition, but
yes, I just
explain without by hiding also.
I don't want to distract you by the second part.
Are you sure it's
It's too
clear when,
complicated.
unless you show actually? Because what you're saying is actually written there, I think.
Yes, I want to prepare you. Okay, so yeah, so if I can find such two polynomials such that for every parameter vector that is not degenerate and every input vector that is not degenerate in this sense, so a value of this function at 0 is non-zero, then if for every such choice, my y, corresponding y, I will say what this means in a few seconds, determines the value of this parameter uniquely. So, because what does it mean? Then you pick a parameter vector and you pick input, then the behavior of state variables is defined because of the theorem from differential equations. The solution exists in analytic functions at a point, and then y is also uniquely defined when you fix parameters and input. In some neighborhood, everybody is uniquely defined. So you have unique function y, and now if this function determines back the value of theta I uniquely, then theta I is globally identifiable. If it determines up to finite number of options, then it's locally identifiable. So if you
So, by the way, so F and G have, or F at least has constant coefficients.
yes, I didn't say that yet.
And the non-constant thing is hidden in U.
Yes, F and G have constant coefficients, and if you have non-constant coefficients, you can hide them in different ways. Actually, you can hide them in X principle. Yeah, okay. So yes, I assume constant coefficients right now.
So why do you choose this as a definition for identifiability?
I wouldn't say that this is my choice. I identify. I mean,
you presented it, so it's your.
yeah. So yeah. Okay. It's yeah.
The point is, I don't see intuitively why this definition says that this particular parameter, if it satisfies these conditions, is actually identifiable.
Yeah, but
it will take a theorem to prove that. But
No,
you see, you're defining identifiable using this method, using this definition. So I want to see that is intuitive at least.
So
Okay.
can you explain slowly.
Yes.
Pointing
For
out
example,
why is what is
for
measured.
example, maybe you will give an example. Are you going to give an example?
I will discuss campuses. So, yes.
No, you gave some very simple examples earlier where some variables are identifiable in one case and the other one
Mhm.
not. Now, would that satisfy this kind of condition?
Yeah. Yes.
Okay, so could you illustrate that?
Yeah. First, may I maybe rephrase what's written here
Could you go back?
to examples?
Yeah, could you actually the request here? So he requested
Okay.
the example.
So
Could you
this
go back
was
one slide more because it shows the system.
That's the
Ah.
easiest one. The one that's not, that's
yeah.
not.
But
so you
just
can-
I want to use the formulas. Okay. So this is the system.
Yeah.
Okay.
Which one do you want to learn, first or second?
Well, you see, to prove something is not identifiable is very hard according to that definition. Because you have to show that for
So
every
which-
No,
P,
no.
Which
for
one do
every
you
P
want?
and every Q, some of them fails.
Yes. So yeah.
To show something is identifiable according to that definition is to produce a P and a Q. Right?
Yes.
Which is in some sense easier because you can search.
Pogudin, which one do you want to discuss now?
So I like first of all to see the one that is identifiable.
Okay.
Okay.
So could you explain this?
Okay. So here in this example,
This one.
we don't have input. Okay.
Okay.
We only have parameters. And for P from definition, I choose. Can you write here? Go
What is Y from the definition?
Y from the definition is Y.
No. The one that you use in the definition.
So yeah,
It's
okay.
not that
So
Y. It's the Y that you wrote in the last line.
yeah,
That's
so
the Y from the definition.
every set of parameters, mu1, mu2, and
Because they're
x,
independent.
yes,
Because they're
x star, they define Y.
Yeah.
So I have a map from parameters to Y. And I want to know if I can go back. So if I can see in Y, understand what parameters were.
So do you confirm that the Y that is written in the last line is the same Y that appears
Yes.
in
Oh
the
yes, oh
definition?
yes.
Yes.
Yes, there's a solution,
Yes,
there's
I
a
do.
solution.
It is a
See, the
solution.
problem is identified, the reason why it's identified is because of the linear independence of the exponential function and one,
Yes, in some sense, this is the reason.
right? I mean, you get 2 points and then you can solve them.
Okay, so
But you see, but how does this being identifiable for mu1 and mu2 fit into your definition? That's what I want to know.
yes, for my definition, I take the polynomial p to be just mu1. So
What was P?
p that says what choice of parameters are degenerate. So for every choice of parameters such that mu1 is not 0.
If you want to use
Then mu1 is
Yeah.
zero.
Okay. So my p of theta in this situation is just mu1. Sorry. So for every choice of parameters, then whenever mu1 is non-zero, I claim. So yeah. So
Yeah, okay.
p of theta. Yeah. So I claim that knowing function y.
Oh, I see. Wait.
Function y is enough to find values mu1, mu2, and x star.
And William, not just this is the case, it is what a modeler would actually accept as a definition.
Yeah, this
Because the question is, based on measurements, can we uniquely find mu1, mu2, and x
Yeah,
star?
so why
Precisely-
isn't that the definition?
This is precisely what's written there.
No, I don't
Knowing why-
understand the example. I understand the example.
Knowing why,
Yeah.
knowing why is what is measured.
Yes.
By knowing why, can you find mu1,
Right.
mu2, and x star?
Yeah,
And
and
it's
I understand
precisely
why. I just pointed it out, that it was because of the independent of the two functions,
Oh,
one
the-
and the exponential
No,
function.
no. The reason why this is correct, why you can find, is a mathematical question about algorithms or about some theory. You're asking about the definition. So
Right.
first, let's address your question about definition.
Right.
Your question about the definition was, why is this a natural definition? Do you confirm that this was your question?
Yeah.
Okay. So he justified this by, well, he explained it by giving a concrete example, and we added. And
Oh, okay.
this is
So,
precisely
so
how
you're,
the model
so,
thinks.
so what you're saying is that the definition is a sufficient condition for that you actually can identify the variables. Is that correct? Because you
No,
have
no.
the theorem. Because you have the theorem.
What do you mean you can identify the variables? I'm not sure. The definition says what.
Definition says that you can identify
So the question, so my question is there an alternate definition that's equivalent to what you just find here?
Oh, there are plenty of alternative definitions.
Not alternate, equivalent, I said.
There are many equivalent definitions.
Okay, good.
Logic, in logic, you modify something that is change the formula.
No,
to
no,
get this
no, I don't mean
equivalent.
that. I mean, intuitively, you said you can solve for the variable. You can plug in a few points and you can find the value of these, estimate these parameters.
Yes, so there is an algorithm that.
But that's what you introduced me to say what is identified.
Please not interrupt. I'd like to answer your question. So there is an algorithm that will, if and only if this holds, will provide, after some computational time, actual expressions
Of
the parameters
all the parameters in terms of the other thing.
in terms of.
So that's why,
it is-
even only if you're saying.
Correct.
Okay, fine.
But
That's fine. Then that's fine.
however, as far as we understand from the modeler's point of view, this is the main definition and not a definition through an algorithm.
So if you have a theorem that's even only if, then why don't you state this as a theorem and then define that, say condition 1 and condition 2 are equivalent, and then if they satisfy that, we call it identifiable.
Because it's not stated that way, because psychologically it's more correct to state it this way.
Why?
Uh,
It doesn't make any sense to me.
It doesn't have to make sense to you to be psychologically correct and to be beneficial for the community.
But what is wrong if you do have an even only if theorem to first state that 1, 2, 3, 4, 5 are equivalent, and then if you satisfy any of this, it's called identifiable.
Okay, let me answer your question.
That's the best way to put a theorem.
Incorrect.
All right.
Because
Your style. Okay, I'm not going to argue your style. Okay,
Can
fine.
I ask a question?
Yeah.
So it looks like in this definition, say you want to show the parameter theta I is identifiable, it doesn't rely on any of the other parameters. Is that true?
Yes,
Yeah.
yes.
Okay.
So you can identify regardless of can you identify other parameters on that
Okay.
canvas?
See,
So then in the previous example, in order to say identify x star or mu2, say, in that example, you needed to first know what mu1 was.
I mean, the way how do you proceed? I mean, so do I understand right that you ask why the way I wrote formulas relied on the previous parameters?
Right.
Yes.
Yeah.
No, this is just a way I show the identifiability.
Right.
So it's a way of
So there's
proving.
a way of
You can make a
Right.
substitution.
Yes.
You can make a substitution.
oh sure, right, yeah.
So but there is a way to access directly me2.
Right, right.
Yeah?
Yeah.
Now,
And let me just so follow up. Richard raised a very good point because for example, this example, the parameter mu1 is identifiable. So the whole model is a bit ill, but the parameter mu1 is healthy. You can find it, and the definition applies to the situation. So it says that nothing is that bad.
Okay. Richard actually prompts me for another question, I'm sorry. But let's go back to the definition.
Okay.
Okay. Now, from what I see here,
William, by the way, this definition is not sort of rigorously finished, written with all details. So he doesn't again say what y is on the slide. So
what do you mean it didn't say what y is?
Yeah, so he talked through it, but he didn't explain it on the slide. What y is.
Yeah, but y is a solution of corresponding differential equation that exists because of the theorem of existence and uniqueness.
Yeah, I know that.
Right. Okay.
I know that you're using implicit function or implicit or the other, but okay. Now I'd like to ask you the last two lines. Is that a conclusion or is it part of the definition?
It's a part of the definition. If the corresponding y determines the value uniquely, then I say that it's globally identifiable.
So the such that has 2 points, actually has 3 points? Is that how I should be reading it or
The
what?
points
No.
are quantifiers.
These bullets are quantifiers, and this is formula. So for every happens.
Can you write down maybe the formula actually as we will work
Okay,
on the paper?
all right, that's better.
And-
That's better,
Do
okay.
you want me to write the formula?
No, okay, I understand. So you see, why I'm asking, Richard was pointing me is that, see, the identifiability is supposed to depend on the system. And if I just look at the first two conditions, that does not.
Then
But you're saying that that's the hypothesis, so that the conclusion has to happen, and the whole thing is identifiable.
Yeah, there is strict
Okay.
where you're looking.
All right, okay.
yeah. So these are quantifiers for every
So,
something.
so that means that, okay, all right.
William, I
No,
have
that's
searched
fine.
through many different ways of stated.
No, I want to understand what it means.
Yes.
Okay? So now I will have a better understanding. Thanks.
Good.
All right?
Yeah, sure. That's great. That's really great. That's great.
So, I mean, see, I was missing the tie. If I just look at the two conditions such that, because it looks, of course, but it is such that if for everything, then this.
It's just for like a logic, like such that.
No, okay.
No, I.
Can you write down the formula?
Yeah.
Formula.
No, I think we're settled on this point. Yeah, just maybe the structure of slide was a little bit misleading, so I just wanted to avoid large mass of plain text, so I wanted to structure this somehow.
Understand.
and
No,
this
that's
structure-
fine, that's fine.
So what is really written is that for almost every theta, for almost every u, then what happens? Theta I
And can you write a formula? What it means? It's
can be.
Yes, no. Or the finite.
I will have to introduce this.
Okay. Too complicated.
So theta I can be read from.
And red
From
form is also
measured.
in quotes. There is a way to formally state it.
Yeah. So this is
You'll see it in the paper. We'll
This is
see.
a bit informal phrase, of course. Like in the paper stated rigorously, just to avoid the explosion of definition.
It's possible and it's not super complicated.
Yeah, it's just some words about functions and.
And the point that this type of definition, to the best of our search through like big search of the literature, is what a modeler would intuitively also think, that this is what it is. And from mathematician point of view, and from the algorithmic point of view, once we see that we get stuck using this definition, so we'll develop some theory to address it.
Now I understand the definition much better, and I understand why it makes a little sense of why it's determinable, identifiable because of the last line. Okay, and I wasn't clear about that. I was just reading kind of the two things because that was the such that, and I thought that was a conclusion, rather than that's also one of the properties of being identifiable in the definition. So that last line actually captures identifiability.
Indeed, yes.
Not,
Yes,
not,
it
not the
does.
2 points there.
No, 2 points are just quantifiers.
Okay, thank you.
Okay, so there are different ways to establish identifiability and non-identifiability. So for local identifiability, that means that you maybe you cannot find the value of the parameter uniquely, but you have just finite number of options. There are fairly efficient algorithms based on computational Jacobian matrix. They go back to some late 70s by Hiram Krenner, and later they were refined and implemented by Sedoglavich and some other authors. So I will not speak a lot about local identifiability because algorithmically this question is more or less solved. And because this measured computation is quite cheap.
Just implicit function.
Yeah, it's just implicit function theory, so you can do it without, for large systems without much problems. So instant thing is global identifiability, and this differs dramatically. So there are actually a bunch of methods that address this problem in some situations and cases. So historically, one of the oldest methods is Taylor series method. I will not go into details. It somehow looks on power series expansions of all these functions. And the issue is that in general, we don't know how far should you expand them. So the method relies on certain bounds. And to the best of our knowledge, there are no general bounds. There are bounds only in some cases. And in these cases, they are sometimes exponential. This is a bit painful for computation. So it's we haven't seen any implementation of this method. So it's
As well.
as well. So it's relies on these bounds that are not that complete, and there is a whole family of algorithms based on differential elimination, and this was actually initiated by this control theory people, Diop, Fleece, and their co-authors, and then brought to the other communities and developed further. So this is, I could feel the whole slide of people who contributed in this area of research. So I mentioned some, just the earliest.
One short question.
Mhm.
Is the condition on the Jacobian matrix one of what you just call finite options?
Yes, yeah. So yeah, this is what I call finite options. This is checked by Jacobian matrix.
So the
Okay.
rank of it is
Yes, when it's full or yeah.
constant rank condition.
Okay, so I want to give a small overview of these differential elimination approaches. So roughly speaking, you can divide them in two different parts, depending on how do you think about parameters. So first part, and historically it is the first, is the following. So let's just return to our system with exponent and shift that we already have seen. What they say that let mu1 and mu2 be also functions, but constant functions. So they say that they're functions, and add two new equations. mu1 dot is 0, mu2 dot is 0. So in this situation, we have just, 1, 2, 3, 4 differential equations, and now we can do differential elimination, compute characteristic set. I will not go into details. There's some sort of algorithms, Rosenfeld algorithm that computes certain representation of an ideal defined by these equations, and assuming that y dot is non-zero function, so assuming some non-degeneracy condition, we have only one characteristic set, and I wrote only part of it, and this part actually gives almost the same formulas I wrote already.
Mm-hmm.
So you can just see these three polynomials as linear equations in x, mu1, and mu2, and you can express them. So, and now you can deduce global identifiability because you have formulas, then it's global identifiable. If you don't have formulas, it's a bit more tricky to explain why it is not global identifiable, and we haven't seen full rigorous proof yet, so didn't find on the sketched proof. So, but okay, anyway, this method works like that, and there are some possibilities to tweak, to speed up it. But the point is that it is still very slow, even for modest size equations. I would say there are. Okay, let me
And
point it.
by the way, so just to maybe possibly explain why it could be slow.
Yes, I will give some reasons right now. Yeah, I was going to explain this.
Okay, so could you please explain?
Yeah. So one reason is why it's slow is that you quite recently enlarge number of variables. So all your parameters are now variables. It's not very convenient for the Rosenfeld-Grobner algorithm at all. And another reason is that the Rosenfeld-Grobner algorithm actually computes much more that you really need, because I have this dot here. I will not use it, and this is the rest of the characteristic set, and it might be actually much larger than the part I will really use.
But not just that, that there are extra terms, but also the first terms give you expressions.
Yes,
And
and
that's, sometimes the customer doesn't ask for expressions. It's interesting to know the expressions for some problems. For some problems, they're just not needed. So question is, maybe can that be avoided? So you see, so that's
yes,
this automatically computes more, and more.
so this is good if you really want these results, but sometimes and quite often you really don't care much.
Well, in general, you probably can get formulas if the mu1, mu2, and the parameters appear nonlinearly.
Oh, we're asking about global identifiability,
Yeah,
so they will be linear.
Yeah. What?
They will be linear expressions.
Right.
If they're globally identifiable,
Yes,
How
they
can
will.
it, look. If instead of mu2 in your y equation, I say I have mu1 times mu2, whether it makes sense or not. Okay. I mean, when you have a system of differential equations and you compute characteristic set, there's no guarantee that variables appear linearly.
no. There is a theorem that says that global identifiability is equivalent to having to linear appearance of
Oh.
variables. Okay, I would say that this.
The definition will require that I can solve for them.
Correct, but it
Yeah.
turns out to be equivalent.
Yes, it's equivalent.
Solving has to be, okay.
Yeah, so we haven't seen full proof of
Well,
this theory, but
we know the fifth degree equation can have a formula to solve it, right? So how do you tell me that you can always solve it?
Well, let's no.
we don't.
I'll show you. You can read the proof and see.
Oh, okay. Well, but
She
you
doesn't
can't.
have
But if you
explain.
can't explain how you can actually solve fifth degree equation,
That's okay. It doesn't apply here.
well, then that's why. So I like to ask why. Why does fifth degree equation?
Well, maybe you invite him for another talk in which he will explain the proof.
No, I don't want to read your proof. I want you to understand why fifth degree equation don't occur.
If you can give us example that it will occur, we will
Oh, no,
with
no,
pleasure
no,
consider it.
no, the burden is on you.
Well, he can decline to answer your question.
Okay, fine. That's fine. Accept it.
Okay.
Okay, so this is the first subfamily of this differential elimination algorithms that treat parameters as variables, as differential variables. Another approach is to say that they are actually coefficients, so we do some differential algebra over the field of rational functions
Okay.
in
You don't
one
mind
and
to
two.
interrupt you since I'm asking the question. The previous slide. Suppose I replace mu2 and write mu3 to the fifth power.
It will not be globally identifiable.
Why not?
Because-
you have to take the fifth root, right? But
Yes,
there are only 5 roots.
but this
You
is
want
locally
unique.
identifiable.
You want unique.
Unique.
See, that explains why.
Okay.
See? Okay?
Okay.
All right, thank you.
Thank you. So,
I mean, because it's unique, so you can't have fifth degree equation.
yes, this is what's written in my definition.
Or if it's fifth degree, it should factor.
So,
Well, no, not only that, you can't. You have, no, actually, this is still unique because it's repeated root.
Pardon?
It's a repeated root. I've mu3 to the fifth power.
mu3.
So it's still unique, right?
Where's
But
mu3?
it's still,
No,
but
it's unique
but it's a
only
degree equation.
in degenerate situation. Then this mu3 to the fifth power will be equal to 0.
No, mu3.
Where's mu3?
Ah, okay, all right.
mu3 to the fifth would be
Mu3
unique,
to the fifth,
but not mu3 itself.
Good. Another question?
But,
So-
but there are situations in which that happens. So, right? I mean, you get a formula for mu3 to the fifth power equal to something.
Yeah.
Yeah, but this is not global identifiable case. This is
Global.
case that can be
That's
made
only
global
global.
identifiable after
Global.
parameterization, but this is another story.
Okay, all right, thanks.
Okay?
So then you can determine then if parameters are not globally identifiable using this method also by seeing if you get them nonlinearly. And-
Yes, yes. So if you don't have these linear polynomials, then it's not global identifiable.
So when you say global, what kind of range do you allow your parameter space be?
C to the n.
Huh? The whole thing,
The whole space over complex
the whole
numbers.
view of complex numbers.
Subtracted a closed subset.
Yes, yeah, the close degenerate
Yeah,
subset.
close constants. Okay, all right. Okay.
Good. So, and the second idea, is to consider parameters as coefficients. And again, now you have just two equations, and you can compute characteristic set again. And I will not write the whole thing. I will just write one polynomial there. Elements of characteristic set that doesn't contain state variables. In this approach, I usually call it input-output equation. Okay, because we don't have input in this example, it's actually output equation. So this formula doesn't give you a way to immediately write what is mu1 equals to. Yes? So, but then you can say that assume that I can measure these two coefficients. Like if y dot and y are somehow independent in some sense, then I maybe can measure these coefficients. And if I can measure them, I know mu1 and I can express mu2. So
Could you explain? So first of all, what you're presenting is not your result, right?
yes. It's
explaining existing methods.
yes. I explain some family of approaches that compute characteristic set or something similar. There are also options.
You're not explaining some detail.
Yeah, so-
you just vaguely explain.
Yeah. Okay. So how does this method proceed? They compute such a polynomial that doesn't include x's, doesn't include state variables. Then they assume that coefficients of this polynomial can be measured. And so if they can be measured, then the next step is to check if you can find formulas for mu's from the coefficients. Like in this situation, I can find formulas for mu1 and mu2 from coefficients. Because mu1 is a coefficient itself, and mu2 is a ratio of two coefficients. So two things that are important here is that I use certain assumption, and I don't touch initial conditions. So now I speak only about mu1 and mu2. So yeah, so this is the outline. You compute equation, and then take the coefficients and try to express your parameters in terms of these coefficients.
Now, the example here, I don't know how, I mean, it is an example, so you do have nonlinear terms, but each parameter is linear. Is that what you mean?
No, I can express parameters as I can express mu1 and mu2 as a rational function in these polynomials.
Are you talking about triangular systems then?
You check.
For the parameters?
Pardon?
For the parameter, you get a triangular system?
You can do it using triangular system.
So we'll
There are-
propose an algorithm to answer that question, right?
Yeah, so you just check that, and you have certain freedom. You can use triangular system, you can use Gaussian basis, maybe you can use something else. It's details, and they differ for different authors.
Yeah.
It is a family of algorithms, it's not just one. Okay, so this approach is in many cases faster than previous one because you take less variables into Rosenfeld-Grobner and you give him less equations. So this is supposed to work faster. There is this second stage, but you somehow divide the problem into stages. It usually helps in computation. However, there are still some issues here. One is that Rosenfeld-Grobner still computes more than they want. So you still get certain formulas, and you still get other elements of characteristic set that you were not interested in. And the second issue is that this assumption that coefficients can be really measured fails in some situations. I just want to show you one of them. This will look a bit artificial. I will explain later what does this example mean in more general context. So this is a system of form that we consider. We have only one state variable, and this is constant. And we can observe this constant, and we can observe some linear combination of some linear function of this constant. So then this input-output equation will be of this form, because you can just substitute y1 instead of x here, and it will get rid of x's. Okay, so, and now the assumption is that you can measure coefficients, and coefficients are actually our parameters. So the method would yield that μ1, μ2 are identifiable. But actually they are not, because let's just analyze the system, because there are no functions, they're just constants. They are not identifiable because you can take any value a for μ1, and then for μ2 you just compute this number. So you take different a's. For μ1, this formula gives you valid values for μ2, and you have infinitely many of them. So this assumption about the observability of coefficients of input-output equation is a bit subtle point for this method. And so what does example mean? What kind of situations does it capture?
Where in your definition on identifiable involve any choice of y1 and y2?
Could you repeat, please?
Where in your definition on identifiable parameters did you say for any choice of y?
I say for any choice of parameter.
No, but no, you wrote for any
Okay,
choice
so
of y1 and y2.
Okay, so
So he's commenting using some equivalent statement. He could also express this non-identifiability using his definition. Perhaps that's a good point to express it. Expressing would amount to solving the system and showing.
So you're already inverting the input-output, is that correct? You're now thinking of y1 and y2 as the input.
So he'll just write down by the definition why doesn't work. It's possible to write in different ways, but since we didn't state the theorem, actually, so and all we have is the definition, then let's just argue by definition. So this is intuitive argument so far because there was no theorem. So
yes.
now
So in order to check this by definition, let's say that if you have fixed some parameters.
So what is y? What is y?
y1, y2.
Yeah.
So in terms of parameters, y1 and y2 can be expressed because we can just solve this equation. Y1 is just x star, it's constant, and y2 is μ1 x star plus μ2. Okay? So now, assume that we picked some values of x star, μ1 and μ2. Okay? So we have values of y1 and y2. And now I take any other value a for μ1